That explains this table we have here. You can see that we had which ones reacted, and so in tube number 1, PbNO3 reacted in the first 3, and NaI reacted in the second 3, so we had access reagent of sodium iodine in the first 3, and access reagent of lead nitrate in the last 3. So here is our data table. Sorry about that. Here's our data table, and we can see up here, it's kind of hard to see, my bad. It's pictures on my iPad aren't great. So we can see that we have the test tubes here, the lead nitrate, the sodium iodine, the height of precipitants, and the max theoretical yield here is what we have. You can see my math for the max theoretical yield here. It's pretty easy. You just take the mole ratio of what you're going to for the geez, I'm totally spacing the name, for the limiting reactant. So like, and you can, it's pretty easy to tell because you know that you're gonna have to have that. You can easily tell the limiting reactant because for the perfect reaction we can see that it's number 3 that has this star little here, is you have to have 2 sodium iodines for every 1 lead nitrate. And so the only one that is going to be perfect is going to be number 3, or should be perfect is number 3, and everyone prior to that is going to have its limiting reagent as lead nitrate, and the 4 through 6, we know the sodium iodine is going to be the limiting reagent. So we do 1/1 for 1 and 2, and then we do 1/2 for 4, 5, and 6, as you can see here. I have to draw in these at another time because I don't have that information. Spencer has it. That is also analysis question number 1. For analysis question number 2, we, as I stated earlier, you can see the number 3 is the perfect yield because, let me get my pencil out, is the mole ratio between PbNO3 and Na2 is 2/1 if you have NaI up top. And you can see in number 3 it's 6/3, which reduces to 2/1. So as you can see, I have filled in the height of precip because I just got that data from Spencer recently, and then I'll show you the graph. So here we see a graph for the max theoretical yield, and in moles, of course. And so pretty much we're using a bar graph of the situation, and we see that as the number 3 has the perfect. Here, let me pull out my number 3. This has the max number of moles that can be created for the reactants that we have, and this also leads me into question 4, and then once I show you the bar graph for the amount of precipitate formed and height, I'll go to number 5. Is for number 4, it says, which tube was there little to no reaction of the supernatant with either PbNO3 or NaI, and what is the mole ratio for this reactant in this tube? So you can see that number 3 is where this should be, because theoretically we should have no access of anything in the supernatant. It should just be spectator ions, but due to human error, we messed up something by a minute amount, so we got a reaction in the supernatant test. But the mole ratio for that is 2/1 or 1/2, whichever one you put on top, or whichever one goes on top. If it's, I believe it's NaI, you have to have NaI on. NaI is 2 and PbNO3 is 1, so if it's PbNO3 on top it's 1 over 2 if PBNI is on top. And then we'll move on to the second half of number 3 and number 4. So here we have the height and precipitate formed in centimeters, and as you can see, it's very similar to the graph of theoretical yield, and that is because it should be. That's the way this experiment works. You can see 3 is the tallest, 2, 4, and 5 are pretty similar, and 1 and 6 are the lower. It's just so our experiment worked really well is pretty much the conclusion, and they are similar. So for number 6, it is write a complete ionic equation for this reaction observed in this experiment, and I'm just going to pause it and do it so you don't have to listen to me mumble while I do the work. So as you can see, here's my net or my complete ionic equation is we have Pb2 plus aqueous plus NO3 minus NO3 2 minus, not 2 minus, but there's 2 NO3s minus aqueous, and then plus Na1 positive aqueous plus I1 minus aqueous yields PbI2 solid plus Na1 positive aqueous and NO3 minus aqueous. And so to make this let's indicate which are spectator ions, and so we can see here that in the reaction the Na and the NO3 are the spectator ions because they do not react. So that for 6b is these two are the spectator ions, and if we wanted to make this just a net ionic equation, I will pause it and show you that. So here we have our net ionic equation right here. We have Pb2 plus aqueous plus I minus aqueous yields PbI2 solid, which is our net ionic equation. Due to the fact we didn't record class data for number 7, I'm just going to kind of go off of a hypothesis and say the inconsistency we had, it was what if other people in number 3, they had different reactants in the spot plate test. Is some had PbNO3 react and some had sodium iodine react, and I think this is just human errors. We can't be perfect in just like a school lab. Is even really good scientists who have like expert equipment, it's really hard to be perfect, and that was just human error that explains the inconsistencies. And then for develop a hypothesis, it says based on the results of this lab, develop a hypothesis to explain how the stoichiometry could determine a reaction that forms a gas, for example, calcium carbonate and hydrochloric acid instead of a precipitate. Well, we know that through stoich we can convert into nearly anything. So if you had, you know that gas is for the conversion factor is 22.4. So it's just it's one of our simplest stoich problems. It's just you go from however much mass you have of, say, calcium carbonate, you have to first write the balanced equation. You go to the calcium carbonate. You have, say, X grams of calcium carbonate. You times that times 1 over the mass of calcium carbonate. Then you multiply that by the mole ratio of the gas you're getting, which is what you want to find, and then you multiply that by 22.4 over 1 because we want to get the amount of gas you have. And so it's pretty much just one of our regular stoich problems that we've always done, and that's just like how we would develop a hypothesis and say that that's the type of problem or the type of things that we can discover through stoich and using like simple math and just the roadmap that we all know and simple mole conversions, we can easily tell what or how much of something we're getting from a reaction. And of course, I pledge, which is I think the last part of this whole video lab. So thank you, and my name is JP. The date is 3/5/15, and my lab partner was Spencer. Thank you. Bye.